So all of you can see the screen, right?
Yes, sir.
Okay, fine. So today we will do some real life perturbation things that actually present in the hydrogen atom. So first of all, so these are basically calculations. Okay, so you first understand the concept, and these are basically calculations. Whatever thing you have heard in your class 12 chemistry or anything you had known of due to the hydrogen or any other kind of atom, splitting of orbitals, splitting of levels, all these things, you will get a hint of it, how it is done. And the actual calculation is I will try to do line by line without stepping out any kind of step. But you look at these notes whenever you are comfortable with. And during the calculation, if I do any kind of mistakes, please feel free to stop me and correct me if I have done anything wrong. So let's start this. I will need some time. Okay, so this uh, hydrogen atom has this so whatever solution of the hydrogen atom we had done previously, that was considering the hydrogen atom was lonely in the sense that it is not perturbed, and there is no perturbation present in the calculation of the of the wave function from the Schrodinger equation, and we separated out. And the algebra, pretty much you all of you knew that we have to do the separation of variables and all those kind of things. And there is but in a real life hydrogen atom, of course this is not possible to isolate a hydrogen atom from the rest of the universe. So there are perturbation present within the hydrogen atom. One class of perturbation is already present within the hydrogen atom which we overlooked, and we will treat them as perturbations on top of the actual solution. And there are external perturbations which you do in labs in order to find out what is the correct nature of the hydrogen atom or correct nature of any other atoms you are studying. So this real life hydrogen atom has two corrections present within the hydrogen atom. So one is the fine structure. So if I am going too fast, please stop me and ask if you have any kind of doubt. So this fine structure is nothing but the relativistic correction plus the spin orbit coupling. So these two are the corrections. And another one is the hyperfine splitting. Hyperfine structure. And this is nothing but the spin-spin interaction. Spin-spin. One spin is for electron and another spin is for a proton. And one important correction that I mentioned yesterday, that we are in the center of mass frame of the hydrogen atom. Of course it is a two body system, but we can go to the center of frame of the system, which is basically the proton, as proton is very much heavy compared to the electron. And we can uh, incorporate this correction by substituting mu by substituting m by mu in everywhere wherever it appears. Okay, so we start with the this relativistic correction. Okay, relativistic correction. Fine. So probably all of you have all of you know little bit of special relativity. I hope so, right? So you're in the third year, you have
Yes,
done
sir.
some course on relativity previously. So yes, so you know that this energy, total energy, is nothing but given in terms of p squared c squared plus mc squared. So wherever I writing, okay, so this is m squared c to the power 4. Wherever I am writing m, if you include the reduced mass correction, you just substitute by mu. So that is the relativistic, and that is the reduced mass correction you have taken into account just by replacing m by mu, nothing more than that. So this is this total energy of a relativistic system, and if you want to find out what is the kinetic energy, you just you just take the rest mass out of it, right? So this is mc square. This m means mass of the electron. Okay, so just make a comment. M replaced by mu. This is the reduced mass correction. And M means Me, which is the mass of the electron. Okay, so and this becomes what? P squared c squared plus m squared c to the power 4 whole to the power half minus mc squared. So this becomes, if we take out this mc squared term common, so this becomes 1 plus p by mc squared whole squared the power half minus mc squared. So mc squared, if I take common, plus half p by mc squared plus n into n minus 1 in by 2 factorial. This is p by mc squared times squared, so this becomes 4, and all those corrections minus 1. This minus 1 is coming from this negative minus mc squared part, so this becomes mc squared p squared by 2 mc squared minus 1 over 8 e to the power 4 mc squared 4 plus this thing. This becomes p squared by twice m. This is the usual part. This is the half m v square part, and then you have relativistic corrections which go up to order 4. This is 1 by 8 p to the power 4. There is a 8 over here. 1 m cancels. This become m cube, and c to the power 8. Uh, Sorry, so I have missed something up.
So the terms
Oh,
will be
sorry,
P
sorry,
by
sorry.
MC. P by
Sorry, sorry,
MC.
sorry, sorry, sorry. So that's why I'm not matching the powers. This is MC, this is MC, and this is MC. So see, when you know the answer, then you can write this p square by 2m. Okay, fine. So this is m cube, and this is c to the power 4 and c squared. That cancels out to be m cube c squared plus order p to the power 6 corrections, which we will not take into account. Okay, so this is this kinetic energy part. So this is kinetic energy including relativistic correction. Relativistic correction. Okay, fine. So see, this part we will take as a perturbation. We will treat it as perturbation. we'll treat it as perturbation. So all of you know what is this Hamiltonian, this H prime in terms of whatever notation we have used. This H prime is nothing but minus p to the power 4 by 8 m cube c square. So this is the perturbed Hamiltonian, and the relativistic correction is denoted by, let's say, R. We will also use the fine structure, so that's why I have denoted by R. While using fine structure, we will use some F or something like that. Okay. So all of you know that up to first order energy correction, the energy correction is written as the first order energy correction is, so previous notation was En1 equals to psi n0 h prime psi n0. So these zeros are in the superscript denoting they are the actual thing. Okay, so let's make it a box. We will use this again and again. Okay, and now what I will do, by using this formula, I will try to find out what is the first order energy correction. I denote it by R, meaning that it is a coming from radiative coming from relativistic correction, and I put it 1 over here to indicate that this is the first order. You will find this psi h r prime psi, and of course there is an index n, and I am suppressing. So okay, so let's write it down. In sorry, the nth state indexing index is suppressed. So we will try to generalize each and every possible solution for any n, so that you can put some value of n and can find out what is the first order correction of n equals to 1 state, 2 state, and so on and so forth. Okay, so this becomes minus 1 by 8 m cube c squared. This is psi, in general psi. This is p to the power of 4. This is psi. Okay, so now what I will do is that minus, I will introduce multiply this 2m thing, which I know that it is the okay, so let's do it p. So this I write it as what else, p squared by twice m whole squared, and I multiply here 2m squared 8 m cube c squared. This is psi. So this becomes minus m squared, and m cube gives you 1 by 2 mc squared. This is psi, and this we can write it as E minus V, because this is the classical part, and then psi. Then we can expand 2mc squared psi. We can expand it as En squared plus V squared minus 2nv psi. Okay. So what we are calculating, ER1. So this ER1. Okay. Then what we can do, this is 2mc squared. This is psi. This En, we keep it as En, because this is the thing we will always try we try to keep, and we'll find perturbations in terms of En, so that we can compare how much large or how much less the comparison is with respect to the original exact En square. Okay, so now this is E squared by 4 pi epsilon 0 squared 1 by r squared minus 2 En E squared by 4 pi epsilon 0 1 by r, and there is psi. Okay, and then we have to extract 2m c squared. En squared is a number, so we can take it out. This is En squared. Psi becomes 1 plus E squared by 4 pi epsilon 0 psi 1 by r squared psi minus 2 En E squared by 4 pi epsilon 0 psi 1 by r psi, and there is a bracket. So this is the expression for ER1. This is ER1. Now you see that in order to find what is the value of the correction, we have to calculate these two integrals, this and this. And you have seen what is the expression for the psi in general n, l, and m. The expression that I wrote, I think in day 4 or something like that. So the expression is quite complicated. Okay, so if you can calculate for any general m involving the logarithm polynomial and all those kind of things, then it is absolutely fine. But the integrals are quite complicated, and you might face any some kind of difficulty using the logarithm polynomial stuff. So what now I will do, I will try to bypass something. uh, I mean, bypass this integral by using a trick that was first introduced by two famous scientists. One of you probably have heard of. So this is the Feynman-Hellman trick. So this thing is known as the Feynman-Hellman theorem. So what this does is finds the expectation values, and this trick you can use anywhere else. Okay, so find the expectation values of different quantities by bypassing some of the usual trick. So in the important thing is it is used for non-degenerate states, and of course we are doing non-degenerate perturbation theory, non-degenerate states. And the theorem is nothing but, so let's say your Hamiltonian depends on some parameter lambda, which is not a coordinate. So this lambda is not a coordinate, is not a coordinate. So for example, in hydrogen atom, for example, in hydrogen atom, lambda can be E, lambda can be N, lambda can be L, and many more, which do not depend on R. So this is a quantity which do not depend on the coordinate, but some any other quantity other than x, y, z, r, theta, phi, and all those kind of things. And your energy can also be a function of this lambda, and as these two are functions of lambda, the this wave function is also a function of lambda. So this Feynman-Hellman theorem states you, so the main statement is, let's say you want to calculate this quantity h del lambda, and it says that it is nothing but the derivative of that, no integration involved. So if we want to find the expectation value of some quantity which is del h del lambda, it says that it is just the differentiation of the energy with respect to the same parameter. So this is nothing stating this. So I will just prove it for you. This proof is very much simple and you can also do it. So let's prove. So this is, so you start with the usual Schrodinger equation. Okay, this h psi n equals to En psi n, and mind that, okay, so let's explicitly write the lambdas, otherwise we will not be able to do any kind of differentiation. Psi n lambda equals to En lambda times psi n lambda. Okay, now what we have to do, we want to calculate this quantity del h del lambda, so we just derivate blindly, we just derivate. So derivating with respect to lambda, so what you will get, del h del, now I am suppressing the units, I mean suppressing this quantity lambda, psi n lambda plus h which is lambda, and del psi n del lambda. Okay, and then on the right hand side you have del En del lambda psi n lambda plus En lambda del psi del lambda n, and you multiply. So now multiply by psi n star lambda and integrate. So what this will give you, so this first quantity, if you multiply and integrate, you will get this psi n star lambda del h del lambda psi n lambda dv volume integral plus psi n lambda h sin star lambda h lambda del psi n del lambda dv, and the right hand side integrate psi n star del En del lambda psi n lambda dv plus this one is En psi n star lambda del psi n del lambda dv. So you can see that the first quantity is nothing but what we want. So this is the expectation value of del h, which is a function of lambda, del lambda plus, so this h operating on psi n star will give you En and will bring out an psi n star because it is an eigenstate, and En doesn't depend on this coordinates, so this is a number, so we can pull it out of the integral. So this En, which is a function of lambda, and the integral is over dv, which is not a function of lambda, and we have psi n star lambda del psi n del lambda dv, and in the right hand side you have del en lambda. We can pull it out of the integral because lambda is not a coordinate and the integration is over coordinate. So this is psi n star psi n lambda dv plus en is, we can pull it out. This is psi n star del psi n del lambda dv. So now you see this term and this term cancels exactly, and this is the normalization. So this is the normalization of wave function, which we set to be 1, and so you have the usual expression, which is nothing but del h n function of lambda del lambda expectation value is nothing but del en lambda del lambda. This is the point we made before starting out this calculation. Now you now look at this. Okay, so so this thing we will use now in order to find. So why did we learn this? We learned this to find what is the, so by we try to bypass this complicated integral involving the logarithm function, the associated Legendre function, and all those kind of things to find 1 by r square expectation value and 1 by r expectation value, right? So this 1 by r square and r expectation value has to fall within this regime, this boxed equation, in order to be useful for us, right? So let's write what is the Hamiltonian. So this Hn, what I have written here, is the unperturbed Hamiltonian. So this Hn, so this Hn, this is the radial part. This H, let's say this is radial. This radial part, if you follow the notes, you will find that the radial part, the u equation, this is h cut square by 2m d2 dr2 plus h cut square by 2m l into l plus 1 by r squared minus, there is the potential, e square by 4 pi epsilon 0 1 by r. Now look at this Hamiltonian and you say that in order to find one expectation values of 1 by r and 1 by r square, what lambda you should choose so that you get your required 1 by r expectation value and 1 by r square expectation value. So let's say we are computing. So let's calculate. So let's calculate expectation value of let's say 1 by r. So now you look at this expression and you say which quantity other than the coordinate you need to choose as lambda, so that you get a you have to do this differentiation with respect to this lambda, and you find with whatever coefficient or constant it has, and you have the main ingredient as 1 by r from this hydrogen, from this Hamiltonian. So one of you can say what is the quantity that I need to choose as lambda in order to use this Feynman-Hellman theorem and get our required 1 by r expectation value. Can any of you say, looking at this radial Hamiltonian of the hydrogen atom?
L.
Del
L.
L. So if you derivative with respect to L, whatever happens, but there is an R square over here, and we are calculating expectation value of R, right?
Yes, sir.
So what we need to do in order, we need to
E.
E, right? So of course you this epsilon 0 is a constant, so there is no meaning that a fundamental constant can be taken as a derivative quantity. So this we can choose as E, right? Because if you look at this expression and if you mentally calculate what is the derivative of the first quantity with respect to E, you will get 0 because there is no E explicitly. The second term, which involves L and R square and H cut square and 2m and all those kind of things, if you derive with respect to E, you will get 0. But the third term, you will have something, but something is not important. You will have the associated 1 by R part. That thing we want to calculate. So by using this Feynman-Hellman theorem, so let's choose what I have done. So choosing lambda equals to E, and using this Feynman-Hellman theorem, we get what? We get del H n function. So there is no n involved, so this is not correct. E, and what it says that del E n, del E, nothing but this. So let's calculate the left hand side. So del H del E, what happens to this del H del E? So the first term derivative with the E gives you 0, the second term derivative with the E gives you 0, and the third term gives you something, and that's something we want. So this is minus 1 by epsilon 0, the squared, E squared derivative give you 2E, and there is 1 by R. It doesn't affect because it is not a function of E, is not a function of R, and you have a expectation value over here, and it says that this is the derivative of En, and we know what is the value of En. En is nothing but, okay, so I have to see this. En is nothing but okay, so what is the value of En? En is, I remembered, but now I forget. E squared by 4 pi epsilon 0 whole square, something like that, and there is minus. Can anybody say what is this? There was a quantity which was going like E squared by 4 pi epsilon 0. There is a whole squared kind of thing, and you had some H cut. Okay, so let's see what is the value. I had written before, so from your previous notes you can see what I have written. Can any of you tell me what is the E?
M by 2h cut.
M by, yes, M by
2h cut.
2H cut, and then
1 by n square.
1 by N square,
Yes, sir.
right? So there is no squared, because I remember there are a lot of squares in denominator. Isn't it AMH cut squared or something like that? I hope so.
H cut square আছে
H squared?
2h cut square.
Oh, H cut squared. So there is no square in the M, right? No square in the M, no?
Nah,
Yes,
sir.
sir.
Okay. Fine. So I actually wrote, so there is a minus, right? So this energy expression has a minus because it is a bound state. Okay, fine. Thank you. So what we have to do? So first we cancel the minus, and then we have, what do you have? We have E by 4 squared. This is 6. Okay, so this is 16. 16 into 2, this is 8. This is pi squared. Please correct me if I am wrong. Epsilon 0 squared, and we need our usual part. This is 1 by r, and then minus minus cancels. This is 1 by 4 pi epsilon 0 whole squared, so this is 16 pi squared epsilon 0 squared, m by twice h card squared. This is there. 1 by n squared, this was also there, and this is e to the power 4, and this gives you derivative of e to the power 4 is 4e cube. So what we have is, so 16 into 2 8, and all this cancels. 8 16 2 4, all this cancels, right? Pi square cancels, epsilon 0 square cancels, and you get e, and this 3 gives you 2, and what happens, and then 1 by r gives you 1 by n square. Have I messed things up? Okay, sorry. So there was no square, right? So there was no squared over here. Fine. So there was no square. That's where I made a mistake. So this is only 4 pi epsilon 0, right? Yes. And there is a 2. And this 2 cancels. Yes. 4, this 4 cancels, and 2 here gives you, okay, fine. So this becomes e by, sorry, twice e by pi epsilon 0 1 by r equals to m by twice h cut squared, and there is pi squared epsilon 0 squared, and there is 1 by n squared. Yes, now it is correct, and there is also e cube. Is there an e cube? Yes. So now you have 1 by r equals to, so this is m by 4 pi epsilon 0 h cut squared, there is an e squared, and 1 by n squared. Yes, now it looks fine. And if you carefully see that this is nothing but the bore radius, so this 1 by r gives you 1 by n square a, where a was our bore radius. This was given as 4 pi epsilon 0 h cut square by m square. Please look and see whether I have done it correctly. So there is also a name. Yes, I have written it over here. Yes, fine. So this is the r. Okay, so this is the r we will use in our expression. And now we have to calculate what is the, so you see this trick is very powerful, and you can use this trick in any of your other problems as well. Where whenever you want to calculate what is the, let's say you want to know what is the general x square expectation value of the harmonic oscillator potential. Okay, so if you use the harmonic oscillator energy eigenstates using the Hermite polynomial, you will face the integral very difficult, because it will have Hermite polynomial squared times the x squared, and you have to integrate it from minus infinity to infinity. If you do not remember the Rodrigues formula and all those kind of things, you will face difficulties while finding that integral. But this you can use in any general case. Okay, So now we will find what is the expectation value of, this is the expectation value of 1 by r squared. Now we will find this, and one of you mentioned that we need to choose lambda equals to L, and using this Feynman-Hellman theorem, we know that del H del L expectation value equals to del En function of L by del L. So what is this? If you derivate it, you will get L times L plus 1. So this is L square plus L. Okay. Now I will try to do it correctly. This is H cut square by 2m. So there is 2L plus 1 if you derivate it with respect to L, and you leave the r square part, and you have an expectation in the left hand side. And while using the right hand side, this is del L, and I will write similarly, this is minus e square by 4 pi epsilon 0. There is a square, right? There is a square. Yes. There is a square, and there is m by 2h cut squared. And if you can remember, this n was found out by truncating the series to a finite number, where we said that beyond this j max there is no state which exists as a part of the solution of intermediate region in the wave function of the hydrogen atom. And then we wrote down n as rho naught, which was defined as j max plus L plus 1. This was written as n explicitly. So this we have to derivate it. So what we do? So we extract out this part, 2L plus 1 by 2m h cut squared, and we need this 1 by r square expectation value. There is a minus. Okay. Yes. There is a minus quantity minus m over 2h cut squared e squared by 4 pi epsilon 0 whole squared. And if you do this, you will get minus 2 j max plus L plus 1 by j max plus L plus 1. This is cube, right? Yes, now it is cube minus 2. Yes, fine. So I have done it probably correctly. No,
The cube is there is 4, sir. I think
there is 4.
the power is
The power is 4.
1 by
Okay,
something
okay,
something 1 by x squared minus 2 by x cube is the difference.
Now it is correct.
Yes, sir.
So now it is correct, right? So you have to derivate x to the power minus 2 with respect to x. So that pulls out a minus 2, and you have x to the power minus 3, right? I have done it right now.
Yes, sir. Yes,
Probably. Yes. Why I messed things up. Okay. So then what you have to do? Then you have to reorganize these things to give you the answer. Okay. So this gives you m square up. Then you have e to the power 4. Then you have 4 pi epsilon 0 squared. So that is 16 pi square epsilon 0 squared. And then you have these 2 and these 2 cancels. This minus and this minus will become plus. There is a 2 over here. So let's write this as 2. And there is an h cut squared. There is an h cut squared. Okay. And then this is no, sorry, h cut square, and there is another h cut square coming from this side. So this is h cut to the power 4, right? Oh, I messed things up. Again, I have messed things up probably. Let's see, h cut to the power 4. Then what we have? Then we have this 1 by, so this is again n. So this is again n cube, and this is 1 by, so this is 2n plus 1, right? I hope I have written it carefully now. And then you can see that this is 1 by r squared, and this total thing can also be expressed. So let's 4 pi epsilon 0 h cut squared. Okay, so this is 4 pi epsilon 0 h cut squared, and this is m is squared, and this is also squared. 1 by n squared, and I divide it by 2 so that it becomes L plus half. And now you get the answer what you are looking for. This is 1 by r squared. Expectation value is equals to, so this is nothing but 1 by a squared, and this is 1 by n squared L plus half. Now I have done it correctly. It matches with the expression. Yes. Yes. You want to tell something?
n cube
N cube? There's n cube? Where? Yes, yes, n cube. Sorry, why have you written n cube? N cube. This is n cube and this is n cube. Yes, yes. Thank you. Yes, so we now have this expression for this 1 by r and 1 by r square, and we have to substitute it. This is a very difficult task to substitute. So now we have to substitute. Where to substitute? Okay, so let's copy it. So this substituting in tab is very difficult. No? This you have to copy. And then you can paste here so that you do not do mistakes. Okay. So this you have, sorry. So this you have, what you have? 1 by 2 m c squared en squared plus e squared. If I mess things up, I will directly just write the answer from the book. So they know what is there. Okay, so this is now 1 by a squared n cube L plus half and minus 2n e square. Okay, I have again messed things up probably. Let's check. No, yes, it is fine. So there is a square. You are not following. So this is, there is a square. Yes, I hope I am right. Yes, yes, there is a square. Because the dimension is not matching, no? There is a square. There is also a squared. Yes. So then 1 by r is what? 1 by r is 1 by n square a. 1 by n square a squared by 4 pi epsilon 0. 1 by n square a. Fine. So you see that there are lots of en, and if you can adjust this en, so let's write this en as minus, so this was e squared by 4 pi epsilon 0. There was a square, there is a m, there was a 2h cut square, and there is a n squared, right? And a was defined as 4 pi epsilon 0 h cut c. There is a c, right? It's an h cut squared. H cut squared by m squared by m e squared. So this is 4 pi epsilon 0 by e squared times this h cut square by m. So then En can be written as e squared by 4 pi squared or whole squared, right? So this becomes what this becomes e squared. Oh, okay. So this becomes h cut squared by m a squared. No, h cut squared by m a squared, and this is squared. Fine. So e squared by 4 pi epsilon 0 squared. This inverted, and this gives you squared. No, there is no squared. Yes, now it is fine. And then there is m, there is 2h cut square, and there is 1 by n square. So you find what is this. So cancels. So this is 1 by 2. Why you are not helping me? Huh? So this is,
Whole square.
so what it happens with respect to a. So this is sorry. So this is this a and this is squared. No, now I have done it correctly.
Yes, sir. Yes.
Yes. Now I have done it correctly. So this becomes 1 by 2 m h cut square h cut square 1 by n square. Is this correct? Is this correct expression? Probably. This is correct, right?
Yes, sir.
Okay. So now what we have to do? So then wherever we get h cut squared, this thing and all this kind of things, we have to substitute it. And h cut square is squared by 4 pi is squared by 4 pi. So this becomes, okay, so let's do it line by line. Minus 1 by 2m c squared. You have en squared plus, so if I replace this e squared by 4 pi epsilon 0 squared, so then this becomes en okay, and there is 2h cut squared by m, and there is n square, and you have to divide it by a square n cube l plus half. Okay, and the second part is 2 en is squared by 4 pi. So this is squared by 4 pi. To replace this thing, is squared by 4 pi n squared e. Okay. So it's squared. So let's how to do it. So 1 by n squared is squared by 4 pi. Squared. Let's keep it as it is. So so you will see that all these things will come out to be of en squared. That's I want to show you. If I miss something, it will not happen. But otherwise, en, and there is e squared by 4 pi epsilon 0. So e squared by 4 pi epsilon 0 is nothing but e squared by 4 pi epsilon 0. E squared by 4 pi epsilon 0 is nothing but what? H cut squared by m squared. Yes, and now again I have 1 by n square a, right? A, yes. See, if I mess things up, you will get the wrong answer. Nothing more than that. But you know that hydrogen atom is hydrogen atom. It doesn't depend on who calculates the thing. So I will just write the answer. Minus 1 by 2mc squared en squared, and then plus and then I have to take care of all these things. So then what happens? Is n squared and n becomes okay. So let's write it down. Otherwise, I will again mess thing up. So this is en. So there is I have to make it as 1 by n squared. So then I yes. So then I put 2. So this is h cut squared by 2m squared, right? So this is h cut squared by 2m squared, and there is an n squared, and everything else I will put it as constant times what happens times. So if I take here n squared, I will have n over here. No, there is L plus half, so let's write it down. Okay, and there is also a 2, so I will have to give here 4, right? I have to give here 4. And then what? 4 minus, so is this correct? 2 4 gives you 2, h cut square is h cut squared, m square is m squared, and there is some tension with the n, and then it is n and n square, and that gives you fine. Oh yes, fine. Now it is fine. 2en, and this h cut squared by twice m squared, so this becomes h cut squared by twice m squared n squared, and then everything else I have to give here. So this is 2, right? Extra 2 I have to feed. Okay, now it is taking shape somehow. Minus 1 by, so now you see this is, so this is e, and this here also is e, so I take en square common. I did all of this just to take en square common, and this gives you 1 plus, this I have taken common, this is 4n by L plus half, and there is minus, I have taken common, so there is 4, right? Yes. So then I have minus en squared by 2mc squared, this becomes a minus 3 plus, this is 4n n plus, sorry, L plus half, right? L plus half, yes. Yes, now we arrive at something which looks familiar with the book, and so what happens is that your en, sorry, en1, the first order correction. Oh, I have written r, sorry. So this r is nothing but en, this is the 0th energy. So this square doesn't mean the 0th energy. Of course, it means the 0th energy, but with the power 2. So there is 2mc squared, and we have 3 minus 4n L plus half. Yes, now it matches. So somehow I got to the answer correctly, and this is the expression for the correction of the first order energy in first order energy due to this. So this is the first order energy correction due to relativistic motion of the electron. Okay, so this is the fine structure, the half part of the fine structure, that is the relativistic correction due to this hydrogen atom, due to this electron moving around the proton with a relativistic correction. Okay, so now we have to do what is the spin orbit coupling. Okay. So the spin orbit coupling is also quite similar. So I have written over here. So this is the relativistic correction. Now we have to do the spin orbit coupling. Okay, fine. We are progressing somewhere. So let's make it this color. Now we will do the spin orbit correction, spin orbit coupling. So any doubt regarding this calculation? I tried to be explicit and somehow I matched. Of course, I did it correctly and somehow I get the right answer explicitly in front of you. So there is no messing around with numbers. So is there any difficulty understanding this calculation or conceptual, any kind of conceptual difficulty you are facing regarding this?
No, sir. No, sir.
Okay, fine. So this is the now spin orbit coupling. So this is a second part of the fine structure. So now in order to do this thing, this spin orbit coupling, so what this spin orbit coupling is? So this spin orbit coupling is due to the magnetic field. So first of all, these are charged objects, right? So these are charged objects, and when they move in a circular motion, so that is they have an acceleration, of course centrifugal or centripetal, whatever you say, they have this acceleration. And you know that accelerating charged particles uh, when they move around a circle or any closed ring, they create an magnetic field. And this magnetic field has this magnetic field of this proton affects the moving electron, which is also charged, because we know that charged particles within this E and B field, they deviate from their trajectories, and all those what will be their trajectory, they will be cycloid or something like that. That was probably done before in electrodynamics. So we will use the spin orbit interaction. So this is the main reason of why we are doing this spin orbit coupling, and it is present within this hydrogen atom. There is no external thing. So this proton is a charged object, it has a spin, and you know the spinning things. So of course the spin do not have any kind of analogy of the classical thing, and the spinning things creates a magnet, and this magnetic field affects a charged particle, and that will give correction to this energy eigenvalues. So what this magnetic field is, so let's write. So what will be this one? So this Hamiltonian for a charged particle in a magnetic field having a magnetic moment mu is nothing but mu dot b, right? So this is mu dot b. So this H. So now I am writing this. So let's explicitly write. So this Hamiltonian of a charged particle moving in a magnetic field is given by minus mu dot b. So this b, what is this b? So this b is the magnetic field created by the proton. So in order to find this, we have to sit on the electron, and if you sit on this electron, you will see the same thing but reversed way. You will see that proton is moving, and it is actually orbiting the electron if you sit on top of the electron. So the magnetic field produced by this proton, if you sit on top of, so B, as seen by the electron. So it sees the reverse thing, right? So it thinks that it is at rest and proton is moving about it. So as seen by the electron is nothing but, so we use this what do you know, this ampere circuital law and all these things. So this is nothing but mu 0 by 4 pi, right? Mu 0 by 4 pi, and this is 1 by r, I by r, and the angle is twice pi, right? So this is mu 0 I by twice pi cancels 2r. Yes, mu 0 I by 2r. So this is the circular magnetic field of a ring that you probably have already derived in electrodynamics. So, and this thing, this is the magnetic field, and so we have to explicitly write this I in terms of the charge and this thing. So what is this charge? So I is nothing but, what is I? So I is nothing but charge by time, right? So this is the I, definition of I, dq dt, right? So this is nothing but I equals to q by t. So this q, okay, so this q is also electric charge, so this t. So now this t we have to find uh, in terms of our known quantities, right? So where do we find t? So this is a circular system which of course has a angular momentum, and this angular momentum we can calculate. So this angular momentum, orbital angular momentum, is nothing but m vr, and m vr can be written as m omega r squared. M omega r squared can be written as m r squared, and this is 2 pi by t, right? I'm doing it right probably. And then t can be found out by, how to find out t? So let's find out 1 by t, because we have to replace it, right? 1 by t is nothing but L by 2 pi m r squared. I'm doing it correctly? Yes, L by doing r squared. Okay, so let's substitute all of this and find what is b. So b as a vector, so this gives you mu 0 by 2 I by, okay, so let's write mu 0 by 2 1 by r, fine. Then I is 1 by t times e times 1 by t is L vector by twice pi, this twice pi m r squared, right? M r squared, and yes, and then we have to organize these things. This becomes mu naught e by 4 pi m, and then r cube, and then an L. So this mu thing, we will substitute it as epsilon 0, and you know the combination that C equals to 1 by mu naught epsilon naught, and there is a root, right? So what happens? This mu C squared, and the 1 by mu is, so 1 by epsilon 0 C squared, yes. So this is mu is 1 by epsilon 0 c squared. So e by 4 pi epsilon 0, and there is a c squared, there is an m, there is a c squared, there is a r cube, and there is a L, right? So this we got from the as an expression for the magnetic field for the this one, magnetic field created by the proton. Okay, And now we have to find this mu. So because h is minus mu dot b, so we have found b in terms of the orbital angular momentum, and we have to find mu. So this mu we have to find. So this mu is the dipole moment. So let's say dipole moment mu is, so what is dipole moment? So this is area times area, right? I times area. And I is, we know what is I. I is q by t. Q is nothing but E by T, and there is area is nothing but pi r square, right? And we have expressed this pi r square over here. So this thing, yes. And in analogy with, so by the way, this spin do not have any kind of classical analogy, but we will try to find it out using S. But you can think it this S as some combination, as some analogous to orbital angular momentum, although it is not strictly true, because we are doing this non-relativistic kind of quantum mechanics, which where spin do not exist. So in order to include spin, you have to do relativistic quantum mechanics, which is nothing but the relativistic some other equation different from the Schrodinger equation, but we will treat this S as some kind of L. And so then A for S equation also we can write the same thing. It is not strictly true, but we will write it for sake of this calculation. So this also becomes m r squared, and there is omega, so omega becomes 2 pi over t. And if you take the ratio, you will find that mu by S, mu by S will give you pi cancels 2, there is a 2 and there is an m, there is 2m, r square cancelled, and there is an e. So this gives you mu as a vectorical quantity. So this is e by twice m into this spin. Okay, so this is the picture that you get. But as I said, that this spin cannot be quantified in classical case, and we do not have any kind of analogy. So if you do it really relativistic correction, so calculation, you will get that this magnetic moment mu is nothing but twice this expression. So this, that becomes E by m times the S. So this is nothing but the relativistic quantum mechanics, which is known as the quantum field theory. So this is nothing but the Dirac calculation. If you really want to do spin in this way, you have to do this fully relativistic calculation of the Schrodinger equation. So the Schrodinger equation has a relativistic approximation, and if you fully want to do this relativistically, you will find spin emerging out as a byproduct of something, of something. So let's not go into that, but you will find that this expression is multiplied, has a factor of 2, and it gives you mu equals to E by m times S. So this is S is the spin of this electron. Okay, so then what is this Hamiltonian? This Hamiltonian we started with H. So now I associate this H as SO. SO means spin orbit. H is nothing but minus mu dot B, and if you put this thing, so you will get E by m and E by 4 pi epsilon 0 E by square, or oh sorry, E by 4 pi epsilon 0, E by 4 pi epsilon 0, and then mc squared, epsilon super 1 by r cube L dot S, right? And then you find that this is E squared by 4 pi epsilon 0 m squared c squared 1 by r cubed L dot s. So this is the perturbed Hamiltonian due to spin orbit coupling. So you can see that orbital angular momentum is L and spin angular momentum is S, and these things get coupled as they have a dot product. Previously there was no combination of L and S, but now it is combined and you have this expression. So this expression HSO is this. So let's make it a box over here. And we have to do the same case. We have to find this eigenvalue of this, expectation value of this HSO to find the first order energy correction of all this thing. And okay, so I made a box over here, but there is something to say that in order to so have you done this Thomas precision in relativity?
No, sir.
No, sir.
Okay, so if you do this Thomas precision in relativity, so this Thomas precision is applied for this thing, because you see this we have done all these things in case of inertial systems, right? But you see this is not an inertial system, because this electron is circularly orbiting this proton. And if you have done this relativity, you know that this non-inertial system can be decomposed into infinite number of this inertial systems, and this correction is related to the Thomas precision, and this Thomas precision factor will also include a half over here, and the correct expression you will get. So this due to Thomas precision adds an extra factor of half, and so let's delete this box and make this copy over here. This will nothing but there will be 1 by 8 pi epsilon 0, nothing more than that. So this takes into account of this thing that we are using relativity, but in case of non-inertial systems. Okay, so this is the correction from the Thomas precision that gives you an additional factor of half. Okay, fine. So yes, now it is fine. So now the task is same. So what we have to do, we have to find the expression for this uh, energy correction. So this is ESO1. So what is ESO1? ESO1 is nothing but psi HSO psi. And you see things are really getting difficult. Now you have to take this expression, what this thing is, 1 by r cube. So previously we had 1 by r square, and now we have 1 by r cube. Okay, so then we have to calculate this 1 by r cube also, and this 1 by r cube can also be calculated. So just before substituting 1 by r cube value, I will have this I will just reduce of how much I can reduce. So this becomes a squared by 8 pi epsilon 0 m squared c squared, 8 pi epsilon 0 m squared c squared, and then 1 by r cube will go into the expectation value, and L dot s. So there is L dot s, and there is psi 1 by r cube, and there is psi. Okay, and this L dot s, what you can do, that you, so there is an L vector and there is an S vector. So this total angular momentum, you call it as J, and you write it as like this: J vector equals to L vector plus S vector. Now you square both these things up, and so let's make it here, and you square both these things up, so you get j square equals to L square plus S square minus 2L dot S. Then you can find L dot S means half of j square minus L square minus S square. And as L has an eigenvalue, you know the the eigenvalue of L squared is L into L plus 1 h cut squared. The eigenvalue of S squared is S into h cut S plus 1 h cut squared. Similarly, if you have this L and L S, so if you have a combined eigenvalue that is J, and similarly it follows the same algebra that you have done. This algebra also has a group theoretic name, but the same group theory follows for J also, and it will have a eigenvalue of j into j plus 1 h cut squared. So this gives you j, so this gives you e squared 8 pi epsilon 0 m squared c squared. There is a half, there is a h cut squared for every h square, l squared, s squared and j squared. And this thing you have j into j plus 1 minus L into L plus 1 minus S into S plus 1 multiplied by this 1 by R cube. I will do this R cube, but let's simplify as much as we can. Okay, so then what, how much we have got? So this we have e squared h cut squared 16 pi epsilon 0 m squared c squared, and then what, and then this large quantity j into j plus 1 minus L into L plus 1. And what is the spin of electron? This is in half, right? So this we can directly substitute as 3 by 4, half into half plus 1, so this is 3 by 4, and you have this 1 by R cube. Okay, so now I will ask you a question. So should I do this 1 by R cube? So because this is non-trivial, because you see with whatever Feynman-Hellman theorem we have done, there is no such thing as R cube in this radial wave function, this what is radial Hamiltonian. So you have to do something more in order to find this thing, but this can be done. So should I write this 1 by R cube expectation value, or you want me to calculate it from the first principle? Because it will take some time, and we need to interpret some results using this spin orbit coupling merged with this relativistic correction will give you the fine structure. So should I do it, or we can just write it down 1 by R square expectation value using the same trick, but you have to do it something more. You have to use the full Hamiltonian, full radial Hamiltonian. Here I have used the differential equation for u. There you have to use the while finding out this 1 by R cube expectation value, you have to use the full Hamiltonian, the radial part. So that involves 1 by R square ddr of R square dr and all those kind of things you have previously seen. So should I do this, or I just write the value and interpret some of the results within 15-20 minutes? So what do you want to do? Because
write
this is
the value directly.
right.
So write the value directly, don't calculate.
Okay, so that's also fine, because see, these are calculation, and you need to do this. I mean, you need to do this once to interpret these results. Okay, so I am just writing it down. So the same. So I just note down some comments. So how to find this finding expectation value of 1 by R cube. So what you have to do is that I just write down the steps. So you have to use the full radial Hamiltonian part. Okay, Hamiltonian part, the R equation. Okay, R equation. Then you have to. So I am writing down the steps. Then you have to why it is not going? Yes, then you have to take the commutation relation of this H red and PR, where PR is nothing but IH cut minus IH cut del R plus 1 by R. This is the radial part. Okay, you have to do this, and you have to take this expectation value of this thing, H rad and PR, and you will see that there will be a piece which is 1 by R cube. You just have to extract that part, and while doing this you have to use 1 by R and 1 by R square expectation value, which we have already derived. So if you do this, you will find that 1 by R square. So if you do this, you will find that 1 by R square expectation value is nothing but this quantity. It is slightly long, but I can write it here. 1 by S squared, no sorry, A cube N cube, and this is 1 by L plus half, and this is L times L plus 1. This you can get if you do these steps. You can get you will find that 1 by R cube is nothing like this, something like this one. Okay, so then I have skipped some of this part, and I have to put all these things over here. Okay, and if you put these things over here, you will find that so let's put it by using this j plus 1 expression. So now E, okay, so change this color. So this is E SO1, right? We are calculating this. So what we have to do, E square H cut squared by 16 pi epsilon 0 m squared c squared. E squared H cut squared by 16 pi. This is the problem with this tab thing. 16 pi epsilon 0 m squared c squared, and 1 by r squared I can replace over here. 1 by a cube in cube, 1 by L into L plus half into L plus 1, and I am missing something. Oh, okay, so the important part. So this is j times j plus 1 minus L times L plus 1 minus 3 4. Okay, so now as the calculation was not done explicitly, so if you do this addition of angular momentum correctly, you will find that this j value, the small j value, can range from L plus half, mod L plus half, to L minus half for s equals to half. So this is the same angular momentum addition algebra that Seth showed you while adding two spins. So previously you had S1 and S2. Previously you had S1 and S2, and you have to add this, and you saw that the value extends from S1 plus S2 mod to S1 minus S2 mod, and the same thing also carries forward over here, and you can find that this j value. So I am now just stating some things. Okay, so you can find it. I am just stating things. So this j value can have two possibilities. So either you have j equals to L plus half, you calculate this thing, and either you have j equals to L minus half. In both these cases, if you calculate this term j into j plus 1 minus L into L plus 1 minus 3 by 4, if you write L in terms of j and explicitly calculate this thing for L equals to half, you will get what you will get is as L, and L equals to j equals to L minus half, you will get minus L minus 1. But you see here, if I substitute L, you will have j minus half, and here if I substitute L, you will have j plus 1. So this is Lj plus half. So this is minus j minus half. Minus j minus half minus 1, right? Yes, minus j minus half. So what you have is this quantity, right? So okay, so maybe I leave it just for L because the answer is in L. Okay, so if you calculate this thing, you will find that this for L plus half you will get L, and for L minus half you will get L minus L minus 1. So now your fine structure is nothing but this addition, right? So this is the fine structure 1 equals to ER1 plus ESO1. And if you do all this thing, this part, you will find that this is nothing but n is squared by mc squared. So I am just stating these things. Okay, so you need to do this. I am just stating these things. So this your this one will have er, what we found er. So let's write it over here for one time. Then for this I just write ESO1. This becomes n en squared by mc squared multiplied this by this quantity L j into j plus 1 minus L into a plus 1 minus 3 by 4, and there is lots of thing over here. L into L plus 1 half L into 1. Okay, so this is the correction to the spin orbit due to the spin orbit coupling. Okay, so let's make it a box over here. So this is the spin orbit coupling, right? So previously I had this first order energy correction due to this thing. And now I have this. So I am skipping some things, okay, because I need to finish. So this is this due to spin orbit coupling. Due to spin orbit coupling. Okay. So now you have to add these two things, and addition is pretty easy because we have already reduced some of these things. So if you do this, all these epsilon 0, h cut, fish cut, all these things, this will give you nothing but n into E naught squared, En squared by mc squared. You can do and check. Okay, so I have done this thing, but you can again confirm and verify. Okay, so now you have this total correction due to fine structure. The fine structure is E relativistic correction plus E spin orbit correction, and this thing was written over here as En squared by 2m c square. Okay, En squared by 2m c squared. Previously you had 3 minus 4n 4n L plus half. These are linear calculations, nothing more than that. And now you have plus all this thing. So we'll find this L j into j plus 1 minus L into L plus 1 minus 3 by 4 by, what is the by, L into L plus half times L plus 1. Okay, so this is the typical thing you do. So then let's calculate it for this for two states. There are two possibilities. The two possibilities are j equals to L plus half and j equals to L minus half. So for j equals to, let's start with L minus half. So then EFS 1 becomes En squared by 2mc squared 3 minus 4n times L plus half by L plus half plus this becomes, what I have written, this becomes L, right? So this becomes L, L and L cancels, and this will give you L plus half and L plus 1. So and there is a 2, but here you do not have any 2, so then you have to multiply this with respect to with 2, because you see there is a only mc square over here, and there is the 2mc square, right? I have not messed things up. So there is the 2mc square, yes. So you have to multiply it 2 while adding, and if you do this thing carefully, you will have En squared by mc squared L plus half L plus 1, and then here you have 2n times L plus 1 minus there will be an, okay, so I missed this n, so there is an n over here, right? So there is an, so this n over here, right? So this n I have to include here as 2n. So is this clear, or okay, so let's write 2n, okay, and then there will be an n over here, and there will be this n. Okay, fine. Then what you do, that you have what you have, you have 2nl, 2n minus n is n, this is En squared by mc squared 3 by 2 minus, so this is n, 2n minus n is n, so this is 2nl minus sorry, 2nl plus n, and if you take the 2 common, you will have 2n L plus half, and this L plus half and L plus 1 cancels, L plus half cancels, and it becomes L plus 1. And you have started with this case for L minus half, so this becomes J plus half, right? So okay, so this becomes L plus half, right? And this will be, so let's make it a page, this will be En, sorry, E fine structure 1 equals to En squared by mc squared times 3 by 2 minus 2n Sorry, I missed something. This one is half, and you see that your L. I I have done something wrong. Oh, sorry. So this is the case for L plus half. Okay. So this is the L plus half case that you. Uh, I have written something wrong over here. Yes, L plus half gives you L. Sorry, L plus half gives you L, and then all this thing you have to do, and you find that if you convert this L with respect to J, you will have J plus half. So the important thing that you need to remember is that now there is N and J. So this is the important thing I want to conclude, that previously in hydrogen atom you have only N where the energy depends on the principal quantum number only. But along with this principal quantum number, now you have also this J, which is a combination of L and S. So now so the important thing to remember is that energy expressions involve N and J. And now you see this quantum numbers N, L, S, Mj, Ml, Ms. These are not, all of them are not good quantum numbers, and the good quantum numbers are what you see over here, that is N, J, Mj. These things are the good quantum numbers. And miraculously, if you do this for L minus half case, so for the same case, so these are just comments I am writing over here. Same expression, you can find it. Same expression, if you put J equals to L minus half. So you put this J equals to L minus half, you find all those kind of things in terms of L, and then you substitute L with J. So for in this case, you will have L equals to J plus half. Previously, you have J minus half, and now you will have J plus half. But you see this expression remains the same. This is the expression. So in terms of L, if you write, these two expressions are different, but in terms of J, if you write, so these expressions are same, and that leads to the conclusion that this expression for the energy eigenvalues have good quantum numbers which are not L, which are N and which are J. So this is the fine structure for this one, hydrogen atom. So just to complete this thing, I write the full expression for the energy. So this full expression for this hydrogen atom is nothing but, so the full energy expression, including fine structure. So what this expression becomes, so this expression becomes ENJ. Now you see J also comes into the picture. You have En, previously that was En, and this En was negative. So in order to make this thing into account, we put a mod over here, and then you had plus, you have En squared. So now we put En squared. Of course, this is mod, and there is 2 m. So if I take 2 mc squared common, then we will have 3 minus 4n j plus half, right, from this boxed expression. And this you have to somehow get to a correct form. So this can be also written as E, if we take En common, if we take minus En mod common, this is 1 and this is En mod by twice mc squared, and this is 3 minus 4n j plus half, and this E mod En by mc squared, if you plug it in, you will get what is the fine structure constant. Okay, so this, okay, so just make it a value. So now, so this ENJ is nothing but minus, so this is 13.6 electron volt by n squared, 13.6 ev by n square. I have written it explicitly over here, and this is 1, this is minus, and this expression you can reduce it by alpha squared by 4n squared multiplied by 3 minus 4n j plus half. So this alpha, what we have done over here, so this alpha thing, what we have done over here is nothing but the fine structure constant. So this alpha by 4n squared, what is this alpha? So let's make it, this alpha is nothing but, so I just write it over here, alpha is nothing but the fine structure constant. So what is this value? H cut c or something like that. There was something H cut c. I have to write it from my notes. So what is the fine structure constant? Do you know? What is this alpha expression for alpha? E squared by something, right? Alpha is so alpha is e squared. I find it out. E squared by e squared. It is written in my note as e squared by 4 pi epsilon 0 h cut c. Yes. So it is this, and this is known as the fine structure constant. So this is known as the fine structure constant. And if you put all these values, you will find that alpha equals to 137. This is a very small number. This is a very small number, and you see the correction in the energy expression is proportional to 1 by 137 whole squared, right? So this is a very small number, and the expression gives you the fact. So you learn two things. So if you include this fine structure, the symmetry, okay, so the thing you encountered previously was your expression for energy depends only on n, and this was previously sometime discussed, that why it depends on n and not L and M, as you introduced in your equation while solving the Schrodinger equation. And at that you have to say that, okay, so this is only independent, but somehow magically this happened, and this magic is due to some symmetry. But in this case, if you include this fine structure constant, which is the radiative correction plus the plus this spin orbit coupling, you break that symmetry and you find that the expression for the energy eigenvalues not only depends on n, principal quantum number, but also g. So this is one fact. The second thing is that the expression for this energy has something proportional to alpha squared. This is known as the fine structure constant, and this alpha is very small. This is 1 by 137, and if you square it, it will be even smaller. So this is this fine structure constant. It shows you that the correction to this original unperturbed hydrogen atom is very small. It is proportional to 1 by 137 squared. And if you really want to do all those calculations involving other things, let's say for the hyperfine splitting and all those kind of things, you will see that every possible correction can be expressed in terms of alpha. So whatever I have done is correct, the expression is correct up to order alpha squared. So you have alpha of up to order. So first what you derive is alpha to the power 0. So there is no correction, that is 13.6 ev by n squared. So this is correct up to alpha to the power 0. Now this expression what you are seeing over here right now, this boxed expression is correct up to alpha to the power 2. So if you include hyperfine structure, you will see that it will have higher powers of alpha, and as you have higher powers of alpha, you can conclude that these expressions, whatever you are calculating, these corrections, these are smaller and even smaller from the original part. So you see our spirit of doing this perturbation theory is correct in the sense that you add more and more to the energy, but the addition is less. So this is something very interesting to note, because if you put all these values for J, L and M, you will find that on top of that unperturbed state, you are adding a very small amount of energy. But this is important. This is important because the experimental hydrogen, what you see, the changes in energy and the atomic spectra, these depend on this expression, because hydrogen do not know you are calculating it is in the unperturbed state or using all the necessary ingredients. It is there, so it will have its own spectra. You need to explain what is the spectra, and if you only do this unperturbed thing, you will get you cannot match all the data properly. The more and more you add this correction, the better you get your results to explain the data. So that's why these corrections are important. So this was the full calculation of the hydrogen atom using the fine structure constant. I thought I would probably end this after the hyperfine splitting, but hyperfine splitting I could not complete, but I will try to manage somehow in between these weekdays, so I will let you know before that. So by the way, is there any date you want to dedicate for this session to include the hyperfine structure and a little bit of Stark and Zeeman effect, so that you can have a clear idea of how much perturbation is there if you include all these corrections? That these calculations are not very much important. This, if you do it not in a hurry, you will find every constant, every factor correct. But somehow I managed to do this with the help of my notes. But if you do it carefully with all the steps written over here and some of the steps I skipped, you will find this expression gets matched to every factor. You will not miss. So these calculations do not matter. But is there any kind of conceptual difficulty you are facing while while we are discussing this fine structure?
No, sir. We have to go through the notes on more time. No.
So do not follow this. I mean, do not follow line by line. Okay, you start with this with something. You start with, let's say you start with this mu dot v expression, and you try and you see your mathematics will be carried forward by your logic. So do not write mu dot b, then substitute mu whatever I have written, then substitute b whatever I have written. You try to do by your own, and you find that your logic will carry forward your calculation. And once you reach this Hn, the perturbed Hamiltonian, then the thing is trivial, right? You have to find the expectation value with respect to the nth wave function. Now this is up to you how you can calculate the nth wave function. You can do it in your usual way with whatever thing you have learned. The expectation value of some quantity is nothing but psi operator psi in a compact notation, this bracket notation. You can do this by this method, or you can do this trick. But this trick is very much useful in your other context also. So you have probably calculated this harmonic oscillator, or you are doing this semester. You calculate the, let's say you calculate the expectation value of x squared in let's say second eigenstate n equals to 2. You do this by your explicit integration, and you do this by this Feynman-Hellman trick. You will find that this will be same. So this is a trick that you need to do, but there is no physics involved over here. Of course, the physics involved is nothing but they have to be degenerate states, and there are some subtleties, but no, not so much deep physics within this Hellman theorem. But the calculation is easy. Once you find the unperturbed, the perturbed Hamiltonian, you have to find the expectation value of that. And finding expectation value is up to you. You want to do this long calculation, or you want to stick to this small. So that is up to you. But this calculation, this calculation procedure is same. You have to find this unperturbed Hamiltonian, perturbed Hamiltonian, and you have to find the expectation value of that. Nothing more than that. And you have to add all the contributions correctly with all the factors to find what is the ultimate expression for this corrected energy. And the important thing is to note that this expression has a factor alpha squared, where alpha is the fine structure. It is a very small, and it is very important also. This fine structure, the measurement of fine structure is very crucial in our field of physics, that is this particle physics. So for extremely precise measurements, you need to know what is this value of alpha to very high degree of accuracy. So this is so to this kind of low energy physics, what you see in day-to-day life, so this value is 1 by 137, but in high energy experiments, this alpha has to be measured very accurately, and this is the main thing that you encounter in this quantum field theory, or this branch of field known as this particle physics. So this needs to be measured very precisely. The more you do this measurement carefully, the more your answers will depend, because everywhere there is a alpha, not only in quantum mechanics but also in field theory. So this measurement of alpha, I want to mention this, but I couldn't get time. So this measurement of alpha is very crucial in this particle physics domain. So this alpha is nothing. So you can think of this alpha as the strength of how much strength an electron has while it talks to a photon or something like that. So I will not go deep into this, but you should keep in mind this alpha is something which we need to measure very carefully, because everything, your atomic spectra, molecular physics, and all these kind of things, you do it from spectra, and the spectra will involve in alpha square. You can see the spectra which Sir has explicitly find out the difference between two energy eigenvalues that will have a Rydberg constant, and Rydberg constant eventually depends on alpha. And you see it has something important. This has an E, and this has 4 pi epsilon 0. This is a constant, H is a constant, and C is a constant. And you might think that E is also a constant, but which is not. But I will not get to that. E is not a constant in high energy physics. So, but in low energy physics, what we deal in day-to-day life, alpha is a constant, 1 by 137. But to a very high degree of accuracy, you have to measure this. So this is quite important in this branch of physics. Anything else you want to discuss, or you want to clarify today's calculation? So can you decide some other day before this week? So is Saturday fine to you?
So Friday.
So Friday I have something. So Friday I have to give some seminar and I have to prepare something. But is Saturday fine to you somehow?
This week Saturday?
Yes, sir.
Yes, so this week Saturday, or
Yes, sir, it's fine.
Maybe in the morning also I am okay. So if it is fine to every one of you, then I can just briefly mention the hyperfine structure and briefly do the Stark and Zeeman effect. Not too much details, because that also involves very much rigorous mathematics. I don't want to get into that, but you should know the actual, ultimate answer. What happens when you apply electric and magnetic field onto hydrogen atom. And the fine structure is due to the spin-spin interaction. Of course, spin is slightly non-trivial. So you need to know the results, what happens to this fine hyperfine structure. So you will be, I do not know whether you can appreciate it or not, but after doing the hyperfine structure, there is some quantity which is measured till date in astrophysics. So that branch is known as this 21 centimeter cosmology. So 21 centimeter is nothing but a transition between two states, and this transition doesn't happen in this not unperturbed theory. So this transition only happens if you take into account the spin-spin interaction of electron and proton, and due to this interaction, your ground state energy splits up into different levels, and these two different levels have a transition, and this transition has a frequency. If you convert this frequency into wavelength, that will become 21 centimeter. And this opens up a new branch in astrophysics, which is known as this 21 centimeter cosmology. So you need to know what is the result. I need to discuss some of this. So if you can give me 1 hour or less, probably 45 minutes to 1 hour in some other day before Monday, I can discuss some of the results. So
Yes, sir. Saturday is fine with us.
so Saturday, from when do you want to?
4:30, like usual.
Saturday 4:30. Okay, so Saturday 4:30 is fine to you. Everyone in this, everyone present today. Is Saturday 4:30 fine to you, or anyone is
Yes,
having any kind of difficulty?
Okay, sir. No problem.
There is no problem, right? And anything you want to discuss from this today? So this is pure calculation. Okay, so this is pure calculation with very much less physics. But you want to discuss anything for today's calculation? So for calculation part, I can assure you, if you do it carefully with no hurry, you will match all the constants. So there is no problem in that. But
Okay, sir.
do you have any query related to any kind of conceptual part? Why this n and j and all these kind of things? Previously you had only n, and now you have l, j, and all those kind of things. Do you have any kind of conceptual difficulty that you need to discuss, or we can end this session now? Is it fine to all?
yes, sir, it's okay.
Okay, fine. So we will meet on Saturday 4:30. I hope I can manage, but if I cannot, I will send you a mail mentioning the revised date, or if there is any kind of change in schedule that I cannot manage on Saturday 4:30. So we will start with this hyperfine splitting, and we will do Zeeman and Stark very briefly, only mentioning the results, and we will end within an hour. That I can guarantee you, that I will not take 2 hours or more. I will end within an hour. So we will meet on Saturday 4:30.
Okay, sir.
Okay, fine. So I am ending this session now.
Okay,
It's
sir.
too much long. It is now already 6:41. So I am ending this. Okay.